But if you do like,
You let us find.
I went up when I was in 11.
No.
What? I mean, I remember when you were 12, you have to like be strong to live in your whole weight.
Sure.
Last Alex.
Where's he going?
All right, folks.
They're writing a diss track on you, him and Alex.
Today, starting chapter 8, talking about probabilities. In my experience, this tends to be a difficult topic for students when it really needn't to be, as the actual mathematics involved don't really go past addition, subtraction, multiplication, division. But you really got to understand like the language and the notation and stuff involved, because things are most likely not going to be presented to you in like the simplest fashion. So you'll be given like story problems and like things with screwy looking new notation. If you don't know what the verbiage means and you don't know what the symbols mean, you're pretty sunk. So again, like the actual mathematics of what you're doing is going to be like, oh, that's it, that's all I had to do. But like the unpacking the language involved to get to that point is the hard part, and that's the part that you really kind of need your attention on. Okie doke? All right. So talking about probabilities. So the idea here is that chance behavior, unpredictable in the short term, right? Like if I flip a coin one time and ask you heads or tails, you know, like which one's going to come next? Well, I don't know. It's like 50-50, right? You guess, it's just a guess. If I flip a coin 10,000 times and I ask you how many heads are we going to get, probably guess around 5,000, and you're probably going to have a pretty good guess, right? You'd expect that to be pretty close to the actual amount. So what you're seeing here is even though that predictable or that chance behavior is unpredictable in the short term, it becomes pretty reliable in the long run. So that's the idea. That's called the law of large numbers. So like here's a little example. This is just the number of times we get heads from flipping a coin, where we flip it like, you know, 1 time, 2 times, 20 times, and then for 500 times. And if you look at the number of heads there, it's a little erratic in the beginning, but it settles down pretty nicely to about 50-50 like you'd expect. Everybody okay with this idea? Again, usually fits pretty nicely into our concepts of like how a probabilistic world works. Now, this being said, this is an important partial credit on quiz or test point. We define a probability as a number between 0 and 1. Okay? You give me an answer that asks for a probability, and you give me a number that's negative. No partial credit. You give me a number bigger than 1, no partial credit. Everybody okay? If you give me a percentage, that's fine. 50%, that's fine. 150%, no partial credit. Negative 50%, no partial credit. Okay? Probabilities are strictly between 0 and 1, or between 0% and 100%. Okay? No negatives, nothing bigger than 1. Okay? Just want to be clear, because if you give me insane answers, there's no partial credit for you, right? Even if it's like you give me some work that gives you an insane answer, you should write, I did some work for this, but it's giving me an insane answer, so I know not to write this down. And I can give you some partial credit for the work that you've done, even if it's giving you an insane answer, as long as you don't report the insane answer. Like, you think that this is actually the answer. You know, at least give me that, like, hey, I did this stuff over here, it ain't right, I can't figure out why it's not right, but I'm not gonna write down that the probability is 2.6 because I know Mr. Gould is gonna give me 0 for that. But the work I have over here is maybe right, and I just was typing my calculator wrong or something. You know what I mean, guys? So you can show me work even if your work is giving you an insane answer. Just don't give me the insane answer as presenting your answer, right? Everybody's good? Okay. So we think that probability seems straightforward, but there's some like typical misconceptions, right? So the first is called the myth of short-run regularity, which just says that, oops, that's not what I wanted to do, that we know probability is predictable in the long run, so we'd expect it to be predictable in the short run as well, right? So like, you know, we say that, you know, flipping a coin, the odds of getting heads are 50-50, right? So we say, okay, in the next 10 flips, I should get 5 heads exactly. No, right? That's not what we'd expect. Now you might say that's the most likely outcome, but you could very well be wrong on that. Everybody agree? Right? You've all flipped a coin before and gotten like, you know, maybe an unpredictable outcome there or unlikely outcome. The other is the myth of the law of averages. So we know that like in the long run, you know, like chance behavior kind of evens out. So like we flipping a coin and last 10 times, or when we're playing, we're gambling while we're doing it, right? Like if it's heads, I give you $1. If it's tails, you give me $1. And last 10 flips, it's come up tails. And I have like 10 of your dollars. You're like, okay, on this next flip, I want to bet $100 that it's going to be heads because it's been tails so many times in a row. It's got to be tails coming, or it got to be heads next, right? That's not how it works. The odds haven't changed on that flip. It's still a 50-50 flip. It's just as likely to come up tails another time in a row as it was before. Everybody okay with that idea? Next thing we want to do is define what we mean by a probability model. All right, and that basically describes like how a specific situation is going to work. So before we can start talking about a probability model, we want to define some stuff first, some terms. So the first thing we're going to define is an outcome. So an outcome is the result of a trial. So if our trial is flipping a coin, there's 2 outcomes that are possible, head or tails. If I flip a coin 1 time and it comes up heads, the outcome was heads. Everybody's okay with that idea? The sample space is the set of all possible outcomes. So if we're talking about flipping a coin 2 times, what are the possible outcomes if I flip a coin twice? What are the possible outcomes? Well, there's 4 possible outcomes, that's correct, but what are they? Heads, heads, tails, tails. Heads, tails, and tails, heads. That would be the sample space if our situation is flipping a coin twice. Everybody's okay with that? To have a probability model, we need two things. We need the sample space and the probability for each outcome. So in our flipping the coin example, what's the probability of heads twice? 1 in 4, right? The probability of tails twice? 1 in 4. The probability of heads tails? 1 in 4. The probability of tails heads? 1 in 4, because we're assuming our coin is a fair coin where heads and tails are equally likely. If you're playing with a cheater, you know, maybe they have a weighted coin where heads comes up 55% of the time or something crazy. They're going to swindle you. Yeah. I think technically speaking, like the American coins, depending on how you flip them, it's like little less than 51% heads because of the way the coin is weighted, because the part of the heads that's on top, you know, like it's like a relief, or maybe it's, I don't remember which one it is, but I think there's like, depending on how you flip it, empirically we've shown the probability of getting one heads versus tails is slightly higher for one than the other. That's neat. All right, so let's look at an example of building a probability model. So our situation is going to be rolling 2 fair die. So your normal 6-sided dice that you play like some Monopoly with. These are Monopoly dice. Everybody good? Okay. What is the sample space going to look like for that? So the sample space is the set of all possible outcomes.
It's going to be like 1 and 2, 1 and 1 and 1, 1 and 2, 1 and 3 for all like 36.
So 36 things, right? So it'd be 1 and 1, 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6. 2 and 1, 2 and 2, 2 and 3, 2 and 4, 2 and 5, 2 and 6, and so on and so forth, right? So you get a table that looks kind of like that. Notice how many outcomes are possible?
Yeah.
36. So the probability of any outcome here is?
1 in 36.
1 in 36. Everybody feel good?
Yeah.
So that would be our probability model. We would list all 36 of these ordered pairs and say the probability for each of them is 1 in 6, or 1 in 36. Now that stinks, but them's the break sometimes. Everybody's okay?
Yeah.
Okay. So again, there's our sample space. Oops. And each outcome has probability of 1 in 36. All right. The next thing we're going to do is define an event. An event is a collection of outcomes. So if we're going back to our rolling 2 dice example, and an event could be the sum of your roll is 2. How many events or how many outcomes are contained in the event the sum of your dice is 2? There's 1 outcome in that event, rolling a 1 and a 1. So the probability of that event is still 1 in 36. Okay? What if our event is the dice add to give us 7? So that event contains 6 and 1, 5 and 2, 4 and 3, 3 and 4, 2 and 5, 1 and 6. There's 6 possible outcomes there. So the probability of rolling a 7 would be 6 out of 36, or reduces down to 0.6. Everybody okay there?
Yeah.
Typically, we name our event, since it's a set, with a capital letter, like the letter A, B, C, D, etc. So if our event is the sum is 5, we go back and we look at that. That is 4 and 1, 3 and 2, 2 and 3, and then 1 and 4, right? There are 4 outcomes there. The probability of each of them is 1/6. If we add them up, that's going to give us 4/30, or probability of each one is 1 in 36. I add up each of them, that's 4 in 36, or 1/9. As an aside here, it says suppose event B is defined as the sum is not 5. What would that probability be? Excellent. 32 out of 36. How did you get that, Ethan? Good. So what Ethan did is use what's called the complement rule. So the probability of not A is going to equal to 1 minus the probability of A. So we'd already calculated the probability of rolling a 5. So not rolling a 5 is going to be 1 minus the probability of rolling a 5. So we did 1 minus 34, or 4 out of 36, which gives us 32 out of 36. Everybody okay with that? That property holds for all probability models, that complement property. Everybody okay? Is it just me, or is it absurdly hot in this room right now?
It's pretty warm.
Okay. Yeah, we need to look at what's going on over here. Stop pumping heat. The heat was set to 74, which I think is excessive. All right. Continuing on. So, what you should have noticed by now when we talk about sample spaces, we're talking about sets. We talk about events, we're talking about sets. What we're going to do now is take a pause here and define some set notation. Some of the notation we're going to use to describe sets. So again, we name a set with a capital letter like A, B, C, etc. And if we want to list the things contained inside of our set, that list needs to start and end with those curly brackets. If on a test I ask you, like, write down the set, for the sum of the dice is equal to 5, if that list doesn't begin with curly brackets, it's a deduction. Are you okay? If you're writing down the stuff inside of a set, the stuff in a set needs to start with those curly brackets, or it's a deduction. Additionally, sets contain no repeated elements. We'll get to a situation where that can come up a little bit later, but I want to mention it now. If you give me a set and it contains like 2 number 3s, that's a deduction. There are no repeats allowed in a set. When we use the lowercase letter n and write it in parentheses around some set, that's like a function notation situation. The letter n of a set is asking you to tell us the number of things in that set. So if my set contains the numbers 1, 2, 3, n of that set is 3, because there's 3 things in it. 1, 2, and 3. Is everybody okay with that idea? We reserve the capital letter U to denote the universal set. The universal set is the entire population being considered. When we talk about probability, the sample space is usually the universal set. The letter O with a slash through it is used to denote the empty set. That's the set containing nothing. The other way to write the empty set is to write the curly brackets with nothing inside of it. Not 0 inside. 0 is something, that's a number, but with like a blank space in between your brackets. Everybody's okay there? Okay. This little curvy letter that kind of looks, or the curvy thing that looks like the letter E, stands for element of, or is a member of the set. So if we say, if we go back to our rolling 2 dice example, if we say our set is the sum of the 2 dice is equal to 5, a member of that set would be the roll 1, 4. So 1, 4 would be an element in the set. The sum of the dice is 5. Does that make sense, guys? If I put a slash through that symbol, that means it's not an element of the set. So for example, if I said 1, 5 is not an element of the set, the sum of the dice is 5. Because 1, 5 adds to give us 6. Is everybody okay there? Okay. The next symbol is that looks like an upside down U. That's the intersection symbol. That symbol is called a cap, like C-A-P. So the intersection is the elements from set A and B that's inside of both set A and set B. So for example, if I have the set A is the numbers 1, 2, 3, and set B is the numbers 3, 4, 5, the intersection of set A and set B is the number 3. But you have to write that with a set. So you have to put a curly bracket around the 3, or it'd be not fully curly. Everybody's okay? The thing that looks like a regular letter U but no tail is that's the union symbol. That symbol's called a cup, C-U-P. The union of 2 sets is the elements that are in either set A or set B or both. So if I have the same set A, 1, 2, 3, and the same set B, 3, 4, 5, the union of set A and B is the numbers 1, 2, 3, 4, 5. Notice that I did not list the number 3 twice, even though it was a member in set A and also a member in set B. Now you're seeing where, like, a situation where I could possibly write down one thing, or a repeated element in a set, right? And the last symbol is the subset symbol. That's like a sideways U. So a subset is a set that's fully contained in another set. So for example, if set A is the numbers 1, 2, 3, and set B is the numbers 1, 2, 3, 4, set A is a subset of set B because all of set A is contained inside of set B. Everybody okay with that idea? Worth noting that every set is a subset of itself, because obviously the set 1, 2, 3 contains the numbers 1, 2, 3, so it's a subset of itself. That's trivial, but worth pointing out. Everybody's okay? Good with the symbols? It's the expectation that you know what these symbols mean when you see them. That would not be given to you, so like you do need to know what the symbols mean and how to interpret them. Okay? So when we start dealing with sets, oftentimes it's going to be convenient to visualize what's going on with what's called a Venn diagram. So when we draw a Venn diagram, we draw a box or a rectangle. That rectangle represents the universal set. Usually we write a little U in the corner, or if it's a probability situation, the rectangle would represent the sample space, so we can put an S in the corner. But if you write a U every time, that's fine. S for sample space, by the way. And then our sets in question, we draw with circles. So here we've drawn the set A with the circle, we've labeled it A. So the part outside of set A is called the complement of A. That's what that little like apostrophe next to the A means in the picture. You guys see that? That means complement. That's not A. That's what that symbol means. Again, do you need to know that? Yes. You need to know what the complement symbol is and what that means. Would I give that to you on the test? No. What the symbols mean would not be given to you. That is your responsibility to make sure you know the symbols. So if we have two sets, A and B, and they have nothing in common, I've drawn those two sets in my Venn diagram. Notice that because they don't overlap at all, that means they share none of the same elements. In that case, we can say three things that all mean the same thing. We could say that the sets A and B are mutually exclusive. They have nothing in common. We could say the sets A and B are disjoint. Again, they have nothing in common. Or we could say the intersection of set A and set B is the empty set. Those three statements are all equivalent. They mean exactly the same thing. You can use them interchangeably, and we will use them interchangeably. Is everybody okay with that? Okay. Okay. If we have if the intersection is not empty, if there is some overlap between sets A and B, the name we give to that overlap is the intersection. We say that overlap is A intersect B. Notice we've drawn the intersection symbol here with the cap symbol from earlier. So A intersect B represents that green shaded area in the picture. Does that feel good? Okay. If I'm talking about the union of two events, remember the union is anything in A or anything in B or anything in both A and B. So the union of A and B is the green shaded region here below. So it contains all of A, all of B, and the overlap between A and B. Everybody's good with that? So far, so good? You guys are super alert. I love it. I suggest here for the way to keep the symbols straight, U is for union, right? The cup symbol looks like the letter U for union. The cap symbol looks like the letter N in intersection. You can use that as a way to remember the two symbols. Okay. Let's look at some examples. Okay, so our situation is we're flipping a coin twice, or you could think about us flipping two coins one time each. That's fine. And record the results. We should represent the sample space in a list form. So our list should start with what? A curly bracket, because our sample space is a set, so it needs to start and finish with a curly bracket. And then the results, or the possible outcomes of our two coin flip we mentioned earlier, heads, heads, tails, 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 heads, heads, tails. So again, that's what our answer could look like. Does the order in which I write those matter? Nope. Their sets are unordered. So whether you write it as heads, tails, tails, heads, 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 tails, tails, or you write it as tails, tails, heads, 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 tails, tails, heads, they're both the same thing. It doesn't matter. As long as you got the stuff in there, you got it correct. Everybody good? Okay. So again, here is we use the U here for universal. You could have also written the letter S there for sample space. Again, when we talk about probabilities, you could use those two letters interchangeably. S for sample space or U for universal set can be used interchangeably when you're discussing probabilities, which is what we're doing, right? Okay. What would we still need to make this into a probability model? The probability model includes two things, right? The sample space, which we have, and what else? Oh, come on, guys, it was just a couple of slides ago. To have a probability model, we need the sample space and the probability of each outcome. Very good. In this case, what would the probability of each outcome be? 25% or 1/4. Yes. And again, you could write them as percentages. You could write it as a fraction. You could write it as 0.25 as a decimal. All of those are correct. If you write percentages, you absolutely need to put a percent sign afterwards. So, okay. I like decimals and fractions personally because it's like one less symbol to write, but you can use percentages. That is okay, but make sure you put a percentage symbol. Because if the probability is 25, you get 0 credit for that because that's a number greater than 1. If it's 25%, now you're talking rational person's answers. We can talk about partial credit or full credit if it's in fact the actual answer. Everybody good? So again, just trying to warn you about the things I'm going to be picky about come quiz or test time, right? That should be helpful, yes? I'm going to keep saying it over and over again. Hopefully it'll sink. Now we could represent the same information in like a table. So you might make like a two-way table where you have like flip 1 and flip 2. Actually, this is just a one-way table. So you can get heads and heads, heads, tail, you know, like it's the same information, just this time it's organized as a table. Everybody's okay? Or you could write as a tree diagram. So this is a really common way of visualizing a chance occurrence. And we'll use tree diagrams a lot because they can really simplify some complicated situations, especially when we talk about conditional probabilities. They're really useful. This situation of flipping 2 coins, it's like you really need a tree diagram, but like I want to introduce what we're talking about. So the idea here is we're going to draw a tree. So each branch of a tree, or where the branching ends, is like one event. So the first flip or the first toss has 2 outcomes, heads or tails. If it's heads, the next part can have 2 outcomes, heads or tails. Or if it was tails, that could have 2 outcomes, heads or tails. So the way you read this is you start at the point and you just follow the path. So one outcome is head-head, another outcome is head-tail, another outcome is tails-heads, another outcome is tails-tails. Is everybody okay with how I'm kind of reading that as what we're talking about? And if the situation is more complicated, the tree diagram can really help kind of ease, make it easier to visualize what's going on. If I want to do this as a Venn diagram, there's not much to do, right? Sample space just got like 4 things in it. Could you have drawn the sample space as a rectangle instead of a circle? Sure, that's fine. I think I used a circle because it was easier to embed inside of the PowerPoint slide here. Okay. As a table, so here I built this as a 2-way table with first toss as like my column variable and second toss as my row variable, and describe the tosses as ordered pairs, where it's first toss, comma, second toss. And this is another very common presentation, especially when things get a little bit complicated, is to describe things this way with a two-way table. Everybody feel good here? Notice that this is all just this representing the same question. What is the sample space in like a bunch of different presentations? Because guess what? In the homework, in the problems, in the quiz, in the test, and everything else, I'm going to present your sample spaces in different ways, right? Just like we've kind of talked about. All right. So let's talk about events here and do some examples with this and how to use these in combination. So let's say we're rolling a standard 6-sided dice, so like a regular Monopoly dice here. And event A is we observe an odd number. If I want to write down in set notation event A, I'm just going to start with A. What do I start with? Ooh, not yet. Bracket. Start with a bracket, and then we'll write down the numbers 1, 3, 5, and we'll end with a bracket. Everybody's good? Again, if you forget the bracket, it's a deduction on the quiz or the test. Okay? This is why I'm hammering it and say it about 40 times here before the first quiz, and still there's going to be like a handful of us that forget them. Ah, I know. All right. Let's say a second question. Let's say we observe a number less than 5. What is the set for event B? Observe a number less than 5. Bracket 1, 2, 3, 4, and then close bracket, right? Yep. How about the intersection of sets A and B? Good. Bracket 1, 3, bracket. Yep. So if you wanted to visualize it as a Venn diagram, you could do that if you have trouble. I think just looking for the stuff in common with both is pretty easy in this sort of situation, but again, presenting you like, what if it was given to you as a Venn diagram and we asked for the intersection? What would you do? You know. Okay. What if we have the event not A? What is that set? Good. Bracket 2, 4, 6. Those are the roll options that are not A. Or if you look at the picture, you're looking at all the things that are not inside of the A circle. Everybody's okay? About A union B. Oh, I'm sorry, A union not B. There's a little, see the complement symbol on the B? So you have everything in A, right? Because it's a union. So it's got to have at least bracket 1, 3, 5. And you also need to include everything from not B that you already haven't included. What are the other, what's in not B? 5 and 6, but we've already written 5, so we don't need to write that again. So this should be bracket 1, 3, 5, 6. Did you guys see it? Remember that the union is the or, so it can be in this one, or in that one, or in both. All those are included. The thing you have to remember about the union is that no repeats. That even though 5 was a member of both sets, we only write it one time. Again, I've said that now, I think the 3rd or 4th time. I'm going to keep saying it every time it comes up because on the first quiz or test, or on the next quiz or test, somebody's going to screw that up. I'd be like, I must have said it 100 times, guys. Like, I don't know what to tell you. All right. Using words, interpret event A. Event A and event B have like specific things. What is going on? What is the event A? Okay, so we would say observe an odd number. That's what we write for A. For the union symbol, we would say or observe, or we'd say or do not observe a number less than 5, or observe a number not less than 5. So you don't want to change it from less than to greater than, because not less than isn't greater than. It's greater than or equal to. Be safe, just add a not. Everybody good? So again, just use, you got to put it in context of the problem when we ask, like, what does that mean in words, right? Saying A and B is like, well, that if you get the or and the not in there, that's partial. But really, I'm looking for like the whole description, related back to the actual thing that's happening. You know? So we did this. All right, so let's look at some rules, some properties that you can use when dealing with these sets. So, A intersect B, guess what? That's the same as B intersect A. It's commutative. A union B, guess what? It's the same as B union A. Those two, I think, should have been no does, Mr. Kulik, right? The complement of A complement is A, right? Like, I'm not interested means like you're interested, right? A intersect the universal set. What's the inner overlap between A and the universal? Universal's everything. So the overlap between A and everything is just A, right? Yep. How about the union of A and everything? It is U, yeah. It's just, well, that's A or everything is just going to give us everything, right? Okay. How about A intersect A complement? What's in A and not A? Nothing, right? How do you write nothing in sets? The empty set, right? Or you could write it as brackets with nothing inside of it. Not a zero inside, but like an empty space. That's acceptable as well. I like using the empty set symbol because it makes me feel, I like drawing the slash through it. I think it's fun, you know. And then I hate drawing those curly brackets. The one on the left always looks pretty good, and the one on the right just looks like a crippled person tried to draw it. I know that's probably not very politically correct, I'm sorry. Maybe it's just like I had a stroke while I was drawing it. There, it's directing at me, not at someone else. All right. How about A union not A? What's in A or not A? Everything, yeah. Because you got A and then everything else. Now these are like fundamental properties right now. There are two special properties that are called De Morgan's laws. These ones are like maybe not totally intuitive. So the first one says the complement of A union B is the intersection of A complement and B complement. So the way I think about this is to distribute the not symbol also flips the union to intersection, right? Like it's negating everything in there. Negates A, negates the union, negates B. The negation of union is intersection. And then if I have the complement of A intersect B, guess what? A complement union B complement. Those are a little less obvious maybe at first glance. If you think about it and you draw a Venn diagram of what's going on, it'll be like, oh yeah, okay, those are the same thing. But that's a little bit harder to see. Everybody good? So far so good? Okay. Let's do some examples. 2 tetrahedral dice with sides numbered 1 to 4. One is blue and one is yellow are rolled. List the elements of the following events. T is equal to the set of dice with at least one die that lands on 3. So to do something like this, I would probably start by like drawing my sample space. And for something like this, I would probably just do like like one of these guys. So I have like 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, and then 4, 1, 4, 2, 4, 3, 4, 4. And what do I want now is anything with a 3 in it. So like that's what I'm looking for, right? So my answer for T would be bracket, and then I'd be like 1, 3, 2, 3, 3, 1, 3, 2, 3, 3, 3, 4, 4. Does that feel good on what I did there to do that? Again, I probably want to enumerate the entire sample space. Blah, 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 blah. And here's basically the same thing that I just drew. So I want those guys right there. There we go. Okay, just the same thing that I just drew a second ago. I think I labeled mine yellow on top and blue on the side. Oh, does it make any difference? No, it's give you the same thing. Notice that what value was only included once in my set, though. Where's the place you could have made a mistake and written it twice? Well, the 3, 3, right? Because if you went down the column and wrote them all down, you went across the row and wrote them all down, it's possible you would have written 3, 3 twice, but that's wrong because how many times are elements in a set? Just once. No repeats. Okay. What about the blue dice lands on 3? What's that set going to be? Just the column 1, 3, 2, 3, 3, 3, 4, 3, right? Everybody agree? Pretty easy. Okay. The sum of the dice is 6. What's that set going to be? Four, 2, 3, 3, 2, 4. Okay, that's it for our presentation. Let's look at some of these in-class examples, though. I'm discarding that table that I drew because same tables later on. Oops, we're not in chapter 14. I sure hope so. All right, let's look at some examples. Suppose that exactly 5% of a specific type of cell phone under warranty will be returned, and the cost to replace the phone is $150. If the manufacturer knew which phones would go bad, they would just charge $150 warranty for those phones and $0 for the rest. However, the manufacturer cannot know which phones will need to be replaced. If the manufacturer wishes to be as fair as possible, how much should the manufacturer charge every customer for their warranty? Who can do this one? I'm going to call some random people here. Hope you've been paying attention. Yeah, I know. Everyone's like, ooh, that wasn't me today. No? Well, then why don't you, for admitting it, you can go first, Trish. Okay.
So,
Probably need your glasses.
yeah.
I'll read it again. Suppose that 5% of a specific type of cell phone under warranty will be returned and the cost to replace that phone is $150. If the manufacturer knew which phones would go bad, they would just charge $150 for those phones and $0 for the rest. However, the manufacturer cannot know which phones will need to be replaced. If they wish to be as fair as possible, how much should the manufacturer charge every customer for their warranty?
I say just charge them $150.
That is definitely not fair. You're making a lot of money.
Lucky or not lucky.
You're a lot of extra there.
Jackson was trying to whisper me the answer. I think he was
Okay. Let's say let's just say we have 100 customers. Okay? How many of them have a phone that goes bad? 5, right? So you should have 5 that are going to be paying up, that you have to pay $150 for. How many have a phone that doesn't go bad? 95. How much do you have to pay for those people? 0, because their phones are fine. Cost nothing for you. Everybody's okay? So you're going to have to pay $750, right? If you average that over 100 customers, becomes $7.50 per customer, right? That is exactly the same thing as what we're doing, because if we take this whole thing and divide it by 100, that becomes 0.05 times 150 plus 0 times 95. That's the same thing, doing the same thing. What is this really the same thing that we've done here? This should remind you of something we've already done this year. It's like the very first thing that everybody was really bad at. Remember when we asked you to calculate the mean and you got a frequency table to go with it? And you have to do like that weighted average thing? This is the exact same idea. In fact, this has a very specific statistical name. This is called expectation or expected value. So if you're a gambler, gamblers in the room, this is critical to being a good gambler. So if you're playing a game and you know the probability of success and how much the jackpot is, if the probability of success times the jackpot is less than the cost to play the game, you should walk away. You will lose in the long run. All casino games are built to have negative expected value because casinos typically don't go bankrupt. You could ask Donald Trump about how that goes. I think he bankrupted 2 of them. Not for gambling reasons. He's not the only one. Casinos go bankrupt. Unbelievably, but they do. Is everybody okay with that? The idea here and what we do? We roll a die 12 times and record the results of each row. Which of the outcomes is more probable? Ethan, what do you got here? Same probability. Why? Why? Well, not quite, because if one of them was 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 12 times, that's much less probable than one of these. Well, how many ones are in the first roll, or the first set? How many are in the second? Okay, how many twos are in the first set? How many are in the second? How many threes are in the first set? And then the second set? Go on and do this for every number. What do you see? The same numbers occur the same number of times, right? Does the order matter? No. Does one of them look less probable than the other? Yeah, this is Mr. Kulik trying to fool you. You're right that the probabilities are the same. They're equally likely. But because the outcomes, it's the same outcomes, the same number of times, the order shouldn't matter to us if we're just flipping or rolling dice. This is one way that you can detect like fraudulent data, is as human beings you try to over-randomize things. And actual random data doesn't look that random to the eye. So this is one way that like experts use to like catch people that made up data. Next one. In casinos, there's often a large display next to every roulette table showing the outcomes of the previous spins of the wheel. The results of previous spins have no effect on the results of future spins. So why do the casinos use these displays? Katie?
Just to like get people to bet, because like they know that they see that and they'll like expect like a certain outcome. It's like the bets.
Yeah, they're tricking you into making a bad bet. Casinos don't do anything that is not making them money. When they give you a free meal, that's to get you to stay in the casino longer because they know the longer you're there, the more money you lose. Right? They give you a free hotel room, they know you're coming back tomorrow to bet some more. It's going to separate you from some more of your money. Nothing they're doing is in your interest. It's all to separate you from your money. Give the probability model for flipping a fair coin 3 times. You may list your sample space in whatever manner you wish. Brooklyn, can you handle this one? Okay, let's start with the sample space, yeah?
Yeah.
Okay.
So we had spin those, but we had spin next to this.
So it's 3 coin flips. So what's one of the outcomes?
Oh, heads.
Well, it should be 3 things, right? Because it's 3 coins flipping.
Oh, right, heads, and then we heads, tails. And then, heads, tails. And then tails, heads. And then tails, heads. And then tails, heads. Isn't that it?
Nope.
Oh.
Maggie.
Heads. Tails, heads.
Oh, yeah. Heads.
How many are we looking for here? Would have been nice to know that in advance.
Like,
8 is the answer that we're looking for. How did I come up with 8? How many options are there for the first coin flip?
2.
For the second coin flip? 2. For the third coin flip? 2 times 2 times 2 is 8. Should have 8 outcomes, which is what we have now, right? Okay. For sample space, that's our sample space. For the probability model, though, what else do we need other than just the sample space? Okay, probability of each outcome, which would be? So I'll just say the probability of x is equal to 1 in 8 for all x in S. So I use some set notation there just to be fancy. You could say that in words, that's fine. All right. Let u equal all the integers from 1 to 10 inclusive. A is the even integers between 1 and 10 inclusive, and B is the numbers 2, 3, 5, and 7. Draw a Venn diagram that relates the given sets above. David! So let me start you off here. We'll do that.
Circle closest to A, we have 2. Yeah, we have 2, 4, 5, 6, 8, 10.
Okay.
Then B, we have 1, 5.
That's a 2.
Oh, so it's then the intersection you have 2, then you have 3, 5, 7. Then outside of it, you have 1. And
Okay. One mistake. Pretty good.
2, where's the 2?
There you go. Good. So my suggestion when filling in a Venn diagram, start in the intersection and then build your way out. So start in the intersection, build your way out. You're less likely to end up with the situation that you landed in where you had accidentally written the same number twice. All right. Use the Venn diagram to shade in the following sets. Blake, can you give how am I going to shade for A complement? Okay. What does A complement mean? Everything not in A. So I would be shading like that. All the stuff that's not. Okay. Can you do B for me then? Now that we did it for you, that one.
B, everything but B.
So it's So what does A union B mean?
Oh, in the middle of A.
That's the intersection. So the union is everything in A or in B or both. Because you want the complement, you want not that. So you want that stuff. You okay? Oops. Tomasino, can you do C, A intersect not B?
Would just be a.
So you're saying this
Without the middle.
out the overlap. Yes, that is correct. Good. How about not A union B? Ellie, can you do that one for us?
Middle. Actually, no, just right.
So you want this part, is what you're saying?
Yeah.
Anything else?
And the outside.
And the outside, okay. Anything else? And the middle. Anything else? That is correct. So the way I would think about this is because it's a union, the easiest way to do it is in 2 steps. So I'm just going to shade everything that's not A. And then shade everything that is B. That's the easiest way to think about it. Unions should be easy to draw because you can just one at a time it.
Right.
Intersections are harder because you have to be careful because you only want the overlap. Jackson, how about E for you?
Be
Everything but the middle. Very good. Yep. So A intersect B is just the middle part. We want everything except for that because it's the complement. That's correct. All right. There are 40 students in an IB school who are studying either chemistry, biology, or both. 25 students study chemistry, 19 study biology, 4 study both. Represent the above information as a Venn diagram and as a 2-way table. How many students are studying just chemistry? How many are studying just biology? All right. So there's my Venn diagram. Maggie, can you help me out filling this in? So you want 15 here? Is that where you want the 15? Okay. 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 Looks okay. Notice that when I look at everything in B, that's 19, right? And when I look at everything in C, that's 25. And 15 plus 4 plus 21 is 40 total. So that's the 0 out there. To represent this as a two-way table, you want to do like one of these guys. So I'm going to have B and not B, C and not C. So this is B and C. That's 4. This is B and not C. That's the 15. This is C and not B. That's the 21. And then this is not B, not C. That's my 0. So how many are studying just biology? 21. How many are studying just chemistry? I put those in there. Oh, just biology is 15. Just chemistry is 21. Goodness gracious. But that's what the two-way table for that would look like. You should be able to go back and forth between the Venn diagram and a two-way table. That would be an expectation come quiz or test time. That if I give you one or the other, you could generate, the opposite one. Everybody's okay? Again, not terribly difficult, but you got to practice it once or twice. All right, there are 50 people in a band. The conductor wants to know who can play the saxophone, the trumpet, and the drums. He finds that 2 people can play all 3. 5 can play just the saxophone and the trumpet. 1 can play just the saxophone and the drums. 3 can just play the trumpet and the drums. 22 play the trumpet. 15 the drums. 18 the sax. Represent the information as a Venn diagram. Marin, this is going to be for you. I waited to give you the big one. You're welcome.
Would there be 3 circles?
Yes. So I'm going to draw a triple here. So we have saxophone, trumpet, drum, universal.
Okay, so you'd have 2 right in the middle of everything.
Yep, the triple intersection.
And then 5 people just play the saxophone and the trumpet. So just 5 people in the S and the T.
Yeah, and notice that you don't have to subtract the 2 from the 5 because of the word just. If that word was missing, if it said 5 people play saxophone and trumpet, then the place where we wrote the 5, we'd actually have to write a 3. Do you see why? So if that word just was not there, where we wrote the 5, we would write a 3. Because we'd already placed 2 people in the saxophone and trumpet circles. But it says just, so we don't have to worry about that. Continue, Marin.
And then 1 person would be in the S and the D. And then 3 people in the T and the D. And then 22 minus 10. There's 12 people in the T. And then 15 minus 6. So that's 9 in the D. Yeah, 9 in the D. And then 18 minus 8. That's 10. Yes. So it's so many people. Okay, so 22 plus 15, that's 30.
Add this way. 10, 11, 20, 3, 5, 30, 42.
Okay, so 8 people in the
Use the Venn diagram to do the count, not the numbers in the list. I saw where you're going. It's like, oh, that's going to be the hard way to do it. Everybody okay with what Marin did here to build our Venn diagram?
Yeah.
All right. Tia, tell me how many people can play no instruments? Yes. All right, Brody, tell me the number of people in S Union T.
Three.
No.
Oh, can't even see that far.
S Union T would be that.
Oh, so. 33.
Yep. And then how about in S Union T? Oh, I did S Union T. Oh, sorry. Then I asked for the probability of S Union T. So that's the number of things in S Union T. What's the probability of selecting someone from S Union T? Well, how many people are in S Union T? How many people are there total?
So, yeah.
33. Let's stop here. We have like a minute left, right? You guys should be able to do the 8-1 homework. I'll get that up on my Notre Dame today. Any questions for me? If you have not answered every single survey on my Notre Dame,
Where am I saying?
so if you go to the very bottom where it says announcements, there's IA surveys as announcement. Click on that. There's hyperlinks on everybody's name to their survey. You need to do that. Everybody needs to fill out every single person's survey. Even if you're not collecting data via survey, the people doing it need your responses to get enough data to make this go. You gotta do it. Get on it. Make some time. Find some time this weekend. Let's come back Monday and be ready to roll with processing some data. Okay? I know, right.